And went through a lot of stuff on waves last class. It pains me that we can't spend more time on that. In fact, one of the semesters I was here at Washington College, I got to teach a course in acoustics, an entire semester just on waves. And we went through a quick survey of waves last Friday. And I just want to remind you of a couple of the major points that are relative to modern physics in the study of waves. Okay. And we spent quite a bit of time doing a problem with Fourier series. Fourier said that if I have a whole bunch of waves that are multiples in wavelength or frequency or period of each other, just harmonics, I can create any other periodic structure that I want. And that's an important idea. And we showed you the issue is what is the amplitude of these harmonics that you put together to create any other periodic structure that you want. That recipe, I proved it. It's Fourier's trick. It becomes some equations that you use. They're calculus equations, and then you're able to figure out what the amplitude of all the harmonics you put together to create a shape is. Okay, we spent some time on that. It's important in modern physics because what we do in modern physics is we model. We think that small particles like electrons, protons, whatever, have a wave character, according to de Broglie, and that wave character is captured in a packet of waves moving through space. All right, so let me just remind you of what Fourier series looks like. I'm going to share the first screen here, which is, yep, Google Chrome right there. And at the top, you're seeing one of the classic Fourier series problems. I add up a bunch of sine waves, and notice it's only the odd harmonics here, and I create a square wave over time. Not animated, but the triangle wave is next. The next one down is animated. You see all the harmonics, not just the odd ones. The interesting thing, though, is the first one looks to be about half the second one. The next one is about a third, then down to about a fourth, a fifth. When you put that particular pattern together, you get what's called a sawtooth wave. Okay, you can see this downslope, then it goes up, and then downslopes again. Okay, as opposed to this square wave where you only had the odd harmonics and it looked like 1/3, 1/5, 1/7. Knowing that amplitude ratio, how the particular amplitudes of each of the waves combine, well, that's key, and that's what Fourier series is all about. But then the last one, probably the most relevant to modern physics, I keep the amplitude the same. I add all the harmonics, and I get what I call a packet or a pulse here. And the more frequencies, the more waves, the more wavelengths I add together, the narrower and narrower the pulse got. Interesting. All right, let's stop sharing this. Neat little animation. And we also looked at just putting two waves together. And I want to remind you of that real quick here. Go back one. I just added two cosine waves. Could have been a sine wave, but I added cosine waves together, and I get a packet that looks like this. And we said, Fourier series, let's just put the packet together, just two here, and we made them equal amplitude. Okay. If I wanted more narrow wave, I would add more waves together. I'd get a narrower packet then. Okay. And we said there's two different speeds that are involved in this. The speed at which the carrier, that blue wave, moves. Okay. And that's called the phase speed. And it's the average frequency over the average wavelength. But then the dash line, the packet itself, the envelope, if you will, that moves at a completely different speed. And that is the difference in the frequencies divided by the difference in wavelengths. And of course, that becomes d omega dk. We call that the group speed. And on this slide, I gave it a V, but because it's just a speed. But by convention, we use U usually for the speed of the packet, the group speed. Okay, and I want to show you that as well. And we'll share. So we were looking here at exactly what we were talking about, two different waves, in this case, two slightly different frequencies. Okay. And the two waves traveled at different speeds. And you can see in this case, both the carrier, the phase speed thing, and the packet, they're both moving to the right. It looks like they're moving at different speeds though. Okay, because there's kind of a change in shape here. And what I want to point out is if I alter the speed of one of the waves, now I got the packet and the carrier moving at exactly the same speed. And I can even, there are everything, the two waves themselves are moving to the right, but by just changing things a little bit, the carrier, the wave itself is still moving to the right. But I think the packet, let's see, the packet, which way is the packet going? Too hard to tell here. Let me change, make it a little more obvious. Yeah, the packet, if you look over to the right side of your screen, the packet is originating over on the right side and then is moving out the left side. And so I've actually reversed the direction of the packet right there. Okay, what the packet is going to the left, I think, and the wave itself is moving to the right. Just watch where it's being created. See, I've got a new packet being created right here on the left side, and it's disappearing out the right side. All right. So that's the question, I guess. So that's the thing we're investigating. We got to finish up our worksheet here today. Stop sharing that and go back to my PowerPoint. And we call this idea that there's a difference between the phase speed and the group speed dispersion. And in case you're wondering, for most waves, in fact, for all waves, what causes dispersion is the material, the medium, wherever the wave is. And as an example of that, in a vacuum or even in our atmosphere, pretty much all frequencies travel at the same speed. And so if it's light, all colors travel at the same speed. If you've got white light, which is the combination of all colors, well, they it stays a beam of white light. Your flashlight doesn't decompose in air into all the colors of the rainbow. It isn't until you run it through a particular material, like the glass of a prism, then in the prism, the material is said to be dispersive, and in the prism, all the different colors, all the different frequencies and wavelengths travel at a slightly different speed, and that creates the wavelengths to be bent at different angles by Snell's law. And so you create a rainbow. Same thing happens in a droplet of water, too. Water is a dispersive medium. Air, we say, is non-dispersive. The speed of all waves, all frequencies is the same. All colors move at the same speed in air. One of the results for a packet is shown on this little slide, where there's a packet created out of many frequencies, and some of them are moving faster than others, and so the packet changes shape over time. And just to keep it in your field of view, we've got it bouncing back and forth, and it broadens out, is what we say. Okay, I guess that's enough on the difference between group and phase velocity, except to look at particles, and de Broglie says they're waves as well. Which speed is the particle going to move at when it's being represented as a wave? Is it going to move at the phase speed, or is it going to move at the group speed of the packet, which is representing a particle? And just use the definitions we said. Okay, phase speed is omega over k. Let's look at what we've been saying about energy, which is Planck's constant times frequency, or h bar, the Planck's constant divided by 2 pi times angular frequency. And what de Broglie said about momentum, that it's equal to Planck's constant over wavelength. I can always go back to that h bar, Planck's constant divided by 2 pi, and you can see it would be, momentum would also be nicely expressed as h bar times the wave number, since 2 pi over the wavelength is the wave number. All right, so if phase speed is omega over k, well, let's see, omega would just be the energy divided by h bar, and k would just be the momentum over h bar. So it looks like a way to calculate the phase speed of a wave, well, of a particle when it's behaving like a wave, is to take the energy of the particle and divide it by the momentum of the particle. That should give you the phase speed. On the other hand, if I'm looking for the group speed, we said it was the change in frequency over the change in wavelength, and the limit that becomes a derivative of frequency with respect to wavelength. I multiplied by h bar over h bar, just it's a constant, and so I haven't changed anything. And so all of a sudden I've got the derivative of the energy with respect to the momentum. And remember, our equation that relates momentum and energy, it's always true, it's just not always necessary to go to these lengths, is this guy right here, back from chapter 2. And from that thing, I want to get the derivative of the energy with respect to momentum. I don't recommend taking the square root and then taking the derivative with respect to momentum. That's the hard way to get that derivative. What I recommend is, since it's squared, and since this is a constant right over here, right, has no derivative, why not take the differential of both sides? And that tells me that 2e times dE, because that's the differential of that guy. And then the differential of this guy right here would be equal to 2p dp times c squared. And then since this is a constant, its differential is 0. It's a little calculus trick, but if I'm looking then for dE over dp, the derivative of the energy with respect to the momentum, because that is the group velocity. And I said we're often going to make that a u. Okay, you'll see I'm kind of schizophrenic on that. I go back and forth. The 2's cancel here though. And let's see, brought that over to that side equation. I got to bring the energy over. So I've got, that's coming over to the other side of the equation. It looks like I've got the momentum times c squared divided by e. That would also be the group velocity then. And so the question is, if I take a particle and I calculate what its speed is classically, and then I use these two expressions right here to calculate the phase speed and the group speed, which one will match the particle's speed? Okay, and so that takes us to the worksheet for last Friday, which we're going to finish up today. And I'm going to divide you up into 2 groups, and we're going to work that problem. And I didn't open up the PDF real quick, so let me pull that open. There it is. I always go to the wrong location. Worksheet. If I'd have been thinking, I'd have had it open for you. There it is. Wrong place, sorry. Yeah, that's what I'm looking for. It always seems that the Finder in Macintosh puts whatever I'm looking for at a different place in the window than where I'm trying to find it. It just seems to be the way it is. All right, so here's the worksheet that we started on Friday, and I spent a significant amount of the class going through showing these are the Fourier coefficients which create this shape, just to make the point that we could create shapes like pulses, like packets out of waves. We didn't get to this problem right here, and we're going to divide up into 2 groups. So now we've got an electron being represented as a wave. It has kinetic energy of 6 eV, and at least for the first 3 parts, we can just pretend it's fully classical. So if I know the energy, I can solve for the momentum. That's A. You can use de Broglie's relationship to figure out what the wavelength is. And then I guess once you got the momentum, you can just divide through by the mass and get the particle speed. And half of you are going to work on that. We're going to go groups. We got 7 people, so we'll have a group of 4 and a group of 3. The other group is now going to look at what is the electron's phase speed operating as a wave and what is its group speed operating as a wave. And we'll see which of these two will compare to get the same answer as part C. And that should hopefully answer the question. If you represent a particle like an electron or a proton or a neutron or some other, or an alpha particle as a wave packet, and we say the packet has 2 speeds, the group speed and the phase speed, which one is representing the actual motion of the particle? All right, so that's the deal here. Half of you do A, B, and C, work together on it. The other half will do D and E, and we'll hopefully get a conclusion here after about 10 minutes of working on this. So let me break into breakout groups here. And I've got 2 groups is what I want. And working on A, B, and C are Justin, Max, Prince, and Shneha. On parts D and E, we have Amaya, Sam, and Saeed. Now, does somebody, yeah, Justin, you've got notability, right?
I just have my regular iPad notes, so yeah, I can.
Can somebody, you can make everybody, I just want to make sure that we've got somebody in each group that can, with the way to work the problem and then display it at the end. I have the ability to move somebody up if we want. Can group 1 handle A, B, and C?
I think so, yeah.
All right, we're going to go for it then. Open all rooms. Everybody see what we're doing? Take about 10 minutes to work these problems, and then we'll come back and we'll go through them and see what conclusion we draw.
Of course, we don't get the ones I already have done.
That's good. That way you get to do the whole worksheet, Sam.
Yeah,
I'm worked
yeah.
out that way. You might not be, but hey, one thing I want to tell y'all before you get started on this, because it may not be obvious, because we're saying, hey, this is classical, right? We're going to show that the electrons are moving at a speed way less than the speed of light. Okay, but where's my little annotate tool here? Come on. It always, I like Zoom in some ways, but then sometimes I don't. Oh, it puts it up there. Okay, so annotate. What is the total energy here? Well, certainly that kinetic energy, which if I remember right is 6 eV up at the top.
Yeah, and then the rest energy.
Yeah, you got to add on the rest energy. And this is going to be 6 eV, right? And this is going to be like 0.511 MeV per C squared times C squared. So you can see that's the big term, isn't it? The kinetic energy in this problem is almost ignorably small. Add it in anyway, just to be careful when you plug in right there. Mm-hmm. Okay, that's the only thing I'll stop you from doing, because I got to be honest with you, the first time I did the problem, I went, oh, energy? Well, I'll just make it the kinetic energy. No. You got to remember the mass also has some energy, because it's total energy when you're doing these problems. Same thing down here. Okay. All right. That's my hint, and I'll leave you alone to do the math then.
All right.
Kind of makes sense also because it's non-relativistic, so kind of together.
I'm
She should.
trying to leave here. I don't want to close the meeting.
You just want to stay.